Thank you, Lou. So hopefully everybody got a copy of the handout, and the handout's just the tasks. I want to start the topic here. I'm interested in students reasoning about proofs of conditional statements, and so you'll notice that there are two statements on the materials I gave you, and then a series of different proofs or disproofs that are related to conditional statements. And I'm going to focus on how students making sense of these relationships between theorem and proof rely on or necessitate the emergence of meanings of conditional truth. And so hopefully that'll all become clear as we move forward. But one of the fundamental problems, so within this task sequence, one of the problems that I really want to sort of surface, and it's not really a problem at first for students, but it's a gap between the way that students tend to think about this situation and sort of normative mathematics, is that according to normative mathematics, this proof is a proof of the converse of this theorem. So this conditional statement, the converse of this conditional statement is also true, so it's a biconditional relationship. And in the normative viewpoint, that biconditional, so if and only if, is made up of two if-thens. And we do not say that this proof proves that theorem. But it's quite common, if you talk with students about this, that they say it does. And so the question is why? So to be able to claim that this proof does not prove that theorem, you need to have some evoked meaning of, well, what does the proof prove and how does it do it? What does the statement mean and how is the meaning of this statement different from the meaning of its converse, even though they're both true? And so that's what I've been investigating, is when I first start off without really much teaching yet, when I get students engaged in this question, what meanings do they bring to the table to try to think about these relationships? And then I do move into a teaching sequence. But in this talk, I'm going to focus on, to some extent, the meanings that I find students bring to the table. And then I won't really get to all the teaching bit in this talk. Although I'm happy to chat about it because I've been thinking a lot about it. And specifically, so hopefully you have some answer to this, but as I move forward, I think with respect to time, I'm not going to poll the audience just yet. I'll talk to you about some of the common meanings that exist in the literature and in my work. So background for the study. So this is really an outcropping of a line of research that I've been doing for a number of years. I guess the first experiments I ran in this strain were maybe in 2014, but I can remember being at the STAR retreat in Utah with Kevin when I first sort of raised some questions that were the seeds of this line of research. So I've been in this for a number of years now. And as was mentioned in introduction, I use teaching experiments, often with sort of a guided reinvention heuristic. And so one of the questions I've been thinking about for a while is, so at the heart of the RME guided reinvention and emergent models set of heuristics for task design is this idea of rooting things in students on mathematical activity. And I had to ask the question, what is the root mathematical activity of logic? If logic is formal, what does it formalize? And what would be the activity that students would engage in out of which they would think about logic? And so with that, what I have done previously is focused a lot on students thinking about the truth conditions for various kinds of statements. So if I give you statements, you tell me if they're true or false. You have to think about the relationship between the statement, its logical form, and then the objects and the concepts that it refers to. And it turns out if you give students the right kind of conditions, they can pretty quickly begin to reflect on their own ways of determining truth and falsehood and begin to develop kind of consciously generalizable truth conditions. And so I've come to call this reasoning about logic, because one of my contentions with a lot of the logic literature is that we look at the way students reason about particular mathematics and then we infer that there's a logic to it. But logic, by its definition, means some sort of generalizable pattern of reasoning. And that's not always something that's at really the heart of what students are doing, or they aren't always aware of it. And so one of my quips has been that logic answers questions that students often haven't asked yet. They don't know what the question is, and so when we teach logical P's and Q's, they don't know what that problem is solving. And so as a result, then I've been trying to be conscious in my experiments about engaging students in task sequences that invite them to reason about logic, where they're sort of considering the question. And I have an instance today in the data of I think, a student apprehending a really powerful question of logic and giving an interesting answer. So either way, there's a little foreshadowing. So one of the other constructs that's come around in my experiments that I've found really productive is what I call reasoning about predicates. And basically this is students or any reasoner's kind of propensity to associate with any mathematical concept the set of all the objects that make the concept true. So anticipating, when we talk about evenness, I can just always anticipate forming the set of all even numbers. Or if we talk about not even, I can anticipate that there is a class of all the numbers that do not have the property, that are not even. Or if I talk about all quadrilaterals that have equal length diagonals, even though I can't maybe easily, I have to maybe work on thinking about what that means, I can anticipate that there is a class of quadrilaterals that have it, and there's a class of quadrilaterals that don't. So I can always anticipate the formation of the whole group of things that have a property and that don't have a property. And so this relates to attaching to any well-formed property, first off, this implicit quantification, universal quantification. Second, being able to, there's a progression of students thinking about not in productive ways through a complement relation, and then also being able to anticipate this even for non-standard predicates. So it's very natural when you talk about squares that students may imagine, yeah, there's all the squares, or they know that there's a class of those things. But when you talk about odd predicates, it's not as natural that students anticipate, oh, well, there's a whole class of things that have it. This turns out reasoning with predicates is just a very propitious way of reasoning for doing logic, because logic tends to kind of build on these ways of thinking. And at the root of it, it's the heart of being able to treat any well-formed mathematical property as sort of having a sameness that it defines a category. That's what logic tends to work on, is just that categoricity, that when students reason in this way, it turns out to be really productive. So let me just give you an example of where this becomes pertinent, just so you can kind of understand a little bit of what I'm working with here. So here's a task that I often give to students, and it appears in the task sequence in the data. I won't talk about it today, but we did it in the same experiments. So I had these students, I gave them 8 representative quadrilaterals. They labeled whether each one was rhombus and or parallelogram. And then I would ask them about what then is the relationship between the group of rhombi and the group of parallelograms. Now the one way to interpret this, if you're reasoning with predicates, is to say that this if then is true because the set of rhombi is a subset of the set of parallelograms. And in fact, this is a generalizable meaning. So every if-then in mathematics can be understood as a subset relation. The truth set of the if part is always a subset of the truth set of the then part. That's one way to think of it. A very common response I get is that students say parallelograms are in the rhombi. And the reason they say that is when they look at every rhombus, parallelogram that property is in it. If you have a rhombi, parallelogramness is in that. And so there's this inclusion in the other direction. And students aren't always playing this out, but there's an interesting relationship. If you list all the properties that parallelograms have, or that rhombi have, and list all the properties that parallelograms have, the set of properties of a parallelogram is a subset of the set of properties of a rhombus. But the set of objects has the opposite relation. There's this sort of back and forth. And so this is just an instance where the students who anticipate forming the set of objects, reasoning with predicates, they will reason differently than students who are maybe focusing on properties. They're focusing on examples and focusing on which ones have which properties, because there's this sort of give and take kind of thing back and forth. So this is where reasoning about properties tends to give this one direction of containment in the way that students construe the situation. And reasoning with predicates gives the subset property. So in the abstract of the talk, I talked about how I'm going to chat about a few meanings for the truth of a conditional and how those have affordances for the kind of teaching learning setting I'm working in. So I want to talk about two. One I've already mentioned is the subset meaning. So that is a meaning of the truth of a mathematical conditional always corresponds to a subset relation. The second one that at least is articulated most easily in the literature by Weber and Alcock is the idea that, so if P then Q is true if Q can be inferred from P. So in other words, if there exists a sequence of valid inferences by which I can infer one from the other, then that's called what they call a warranted conditional. And that's very related to, but somewhat separate from, what I want to do in the next bit of the talk is talk about, if you look at common intro to proof textbooks that teach the logic of conditional truth, what's the meaning that textbooks tend to convey? So it's not quite either of these, although it's a little closer to the warranted conditional. So I'm going to take a moment to consider the meanings that textbooks endorse. So this is an excerpt from a nice intro to proof textbook that you know I'm pleased with, if nothing else, because it's free online. And so what they do is they introduce a conditional statement. So if you're a multiple of 6, then you're multiple of divisible by 2. I don't know why the asymmetry here. And then they very explicitly break that into, it has 2 parts. And so this is an if-then relation between those 2 parts. But in the end, then, here's the bit where they say, well, what's the statement mean? What do we mean by saying it's true? So they first off say this, we're going to shorten the if-then language into a symbolic relation between P and Q, just an arrow. And that has a specific meaning. So when we assert that P implies Q is true, we mean that if P is true, then Q is true. Now, to some extent, that's sort of just circling back to what we started with. But on another way, there's this notion about toggling truth, when I assign it to be true. And you just think, okay, well, what do we mean to assign it to be true? And there's some real problems. I have a recent paper where I discuss why that's a bit of a funny framing for the way students interpret this sentence if we just give it to them. But then it goes into this other idea of forcing. P being true forces Q to be true. And again, you say, well, okay, well, what meanings does that evoke, this forcing? So we call it a conditional, and then there's another restatement, Q will be true under the condition that P is true. And all these are just rewordings, but again, what does it really convey? And very quickly, so this relates to what's often presented as what we call a truth functional meaning. That we talk about possibilities of when the two are either true or false together. And classically, we claim that mathematical conditionals, what this sentence means is that it will never be the case that P is true while Q is false. That's another meaning, the truth functional meaning. That you'll never find an example where this is true and that's false. That combination doesn't happen. And that's the material conditional. And kind of interestingly then, in the very following exposition, it goes on to present, in wanting to build towards biconditional statements, it shows converses, and then points out, because in this case, with these 2 predicates, one is true and the other is false, that tells us a general fact that because, again, one of these is false for 4, therefore the meanings of P implies Q and Q implies P are generally quite different. The conditional statement is called the converse, and its converse express entirely different things. What I don't see here is, have we given them a clear way to distinguish what do they convey that's different? This text, all it does is says, look, in this case, this one's true and that one's false, so therefore they can't be the same. So what this is an example of is what I'm calling the fundamental warrant of logic. So logic, by its nature, we assume that we are looking at the form of statements, and we want to know what can we say about the truth and falsehood of statements based only on their form. So as soon as we insert a P and a Q, we are assuming P and Q, whatever they actually mean, is irrelevant to whatever we're doing from here on. And therefore we're generalizing across all the possible values of P and Q. Therefore, when you're playing the game of logic, here's basically the argument. If one argumental form so an argument of a given form is only valid if all examples of the argument with true premises have true conclusions. So in other words, if all possible assignments of P and Q produce acceptable arguments or have false premises, then that's a valid proof type. Now, this is stated in a really funny general way, but let me give you some implications of how we really use it. But the consequence of this is if you give me a single argument of a form that is somehow problematic, then that invalidates all other arguments of that form. And my question to you is, do we expect students to find this as a natural fact? I mean, this is an interesting kind of generalization, but let me give you some examples of where we use it. Because this particular conditional and its converse are non-equivalent, therefore no conditional is equivalent to its converse. Right? That's what the book did. Because I gave you one example that fails of that type, you must ignore all other instances of that type. Another example we commonly give, here's an example of an inductive inference that's true for 1,000,000 cases but fails in the 1,001st. Therefore, don't trust any inductive evidence ever. It's never trustworthy. And we make these arguments, don't we? And my claim is those arguments implicitly rely on the fundamental warrant of logic, that we generalize across the form of the argument. Okay, so pack that away, it'll come up in the data later. Okay, now to the current study. Where am I doing on time? Oh, hey, I'm doing well. Moving up in the world. Okay, Kevin knows how bad I am at time management talks, but I really would like to say I've made improvement in recent years. I have to admit it's getting better. Getting better all the time. Okay, so what am I doing in the current study? So I recruited pairs of Calc 3 students. The task sequence is sort of like what you have in front of you. I presented them with a conditional statement and then a sequence of possible proofs of related facts. And all the proofs are correct, but not all the proofs are about that statement. And the task that I give the students is to determine, does that proof prove that statement? Why or why not? And if that proof does not prove the given statement, what does it prove? And so at this point, the way I'm sort of shifting the game a little bit is their question is really to determine what's the force of the proof. The proof proves something. I try to guarantee there's no errors, there's no mistakes. But what does the proof prove and why? How does a proof prove a general claim? The proofs I gave them, the way I generated them, was pretty, I guess not all that clever, but it was pretty systematic. So I would always give them, not always in this order, but direct proof, proof by contrapositive, and then if the converse is false, I'd give a disproof of the converse. If the converse, is true, I would often give a proof of the converse. And similarly, a couple times I also give them the inverse, which if you're not up on your logical language, so if P then Q, converse is if Q then P. Inverse is where you add nots to both, so if not P then not Q. And contrapositive is where you do both, you switch the order, add nots, and that actually is always equivalent. So if the conditional is true, the contrapositive is true, and vice versa. Okay, so that was the way I produced the proofs. So students would see as many as usually 3, maybe 4 proofs of each, related to each statement. And then the first couple tasks, as the ones I gave you, were related to number theory relations, divisibility relations. And then after that, we went into geometry tasks, and then we've generated some other tasks, but we usually haven't had time to go too deep into much more. Okay, in the recruitment process, we gave a pre-screening survey. So my colleague Kyung-ha and her colleague Lee developed this. They measure what they call it cognitive conflict, but they give students 3 groups of 3 tasks. Here's a proof of a statement. And you ask them, is this a valid proof or not? is this proof trying to prove the statement true or false? And do you believe the statement is true or false? And a student has a cognitive conflict if they say these combinations. I think the statement's true. This proof is trying to prove it false, and it's a valid proof. Or if they say, I think the statement is false, the proof is trying to prove it true. And it doesn't. Either way, do y'all see the idea? If I think here's a acceptable, valid proof that proves one truth value, and I believe it has the other truth value, they call that a conflict. And the basic thing is we wanted to find students who had these to justify that there's a, we don't expect them to have really fully worked out these relationships ahead of time in the teaching experiments. This is the way we have found some pre-evidence that the students needed to kind of work through some of the topics that were at the heart of the teaching experiment. Okay, and usually out of 5 of these possible conflicts, a high number for a student to express is 2. Most students don't do this a lot, but still we had participants who had as many as 2 of these conflicts. And we only recruited students with at least 1. Okay, so here's the basic hypothesis that we're working from in the teaching experiment, which is, and the teaching experiment sort of proceeds with the first few tasks are really just task-based interviews. We just kind of let students bring to the table whatever meanings they have. And so the data I'm going to present now is really without much of me teaching explicitly. It's just sort of what do they bring to the table. Then we go into a teaching sequence focused on reasoning about predicates, and then we try to go back and see how they leverage those ideas. That's the total cycle. But what I'm going to present on is really the initial part where students are bringing out whatever meanings they will. But the key idea is that they really can't answer these questions about what does the proof prove without at least drawing on some sort of meaning for the truth of the conditional. And it may not be that they can state it in general form, and I'm not assuming this is the meaning they have for all conditionals, but they need to evoke something. They need to draw up some kind of meaning for truth to be able to relate these proof statement pairs. And moreover, especially for them to actually resolve that problem that I presented at first in the normative way, for them to be able to say this proof of the converse does not prove the original conditional, they especially need to have some explicit meaning for the truth of the conditional. What does the conditional say apart from its converse? And so this is what we want to investigate, is the meanings that the students have, and then also how do those afford and constrain their sense making, and then finally how can we teach them what we would consider productive meanings. And so in the long run, our goal was to develop the subset meanings. So that's the meaning that we are trying to target. And that has been, yeah, I'll just leave it at that. That's the meaning we wanted to develop over the course of the teaching experiment as a whole. But we're also open to observing what students bring to the table that seems productive for them. And I'll give you one instance today of where a student actually had some really powerful reasoning that was not the subset meaning, but it operated productively for her. So, okay, so I'm going to share mostly stories from a particular pair I'm going to call M and A. I didn't name them A and M because now I'm back in Texas at a different school, so I guess I'm not supposed to like them or something, but y'all aren't supposed to like them either now that they're in the SEC. I don't know. Either way, so M and A. No, A and M, whatever. So they were computer science. They were computer science majors taking Calc 3 together when they took part in the study. The computer science bit was actually pretty important in how this came out, because with these initial tasks that are all about divisibility, it turns out their experience with modulo division gave them really rich meanings for divisibility, and also thinking about remainders, how you could partition all the numbers according to the remainders. That was pretty rich for them. And so this pair made much faster and much more kind of productive progress than the other pair that we've gone through this with so far. And so I'm going to give you a quick run through. We really got to the question at hand by the end of the second day of the teaching experiment. But I'm going to give you a quick run of just some observations about their reasoning through the first task and then the second task, leading up to the consideration of proof 2.2. So first, thing that, we haven't done this with a ton of students, but something that seems to come out pretty quickly. Students notice that the first line of the first proof matches the if and the last line matches the then. And the second proof has the opposite. The first line matches the then and the last line matches the if. They notice that mapping pretty quickly. That's something that comes out pretty naturally. And on the first proof, this is pretty productive because they say, oh, well, the first proof proves the theorem because it goes from if to then and it's true. The second proof is often showing that it doesn't work the other way. So for instance, let me first talk about an interesting thing M did. So look at line 3 of proof 1.1. So in proof 1.1, you pick an arbitrary element of the multiples of 6, call it x. You apply the definition to say x divided by 6 is k. And then what you do is you want to show from that equation that x over 3 is an integer, right? So this is the standard proof method. So the first there, so after thus, it says x over 3. M did this real interesting thing where she said, well, if they write x over 3, that's like you're assuming your goal. She said, does that mean that x is divisible by 3? Now this is really common because students' meanings for divisibility are often somewhere in between a property of the number and an operation to be performed. Divisible by 3 often evokes for them the notion of I will divide by. And that's part of why M, when she sees x over 3, she takes that as almost an assertion of divisibility by 3, as opposed to simply raising the question, or however you want to rhetorically think about what that equation means. But what's notable about that, notice, is she's already thinking in a quantified way. She's saying, well, x over 3, if that means it's divisible by 3, because very quickly what she said is, not only is that assuming the goal, she said very quickly, I know some multiples of 3 are not multiples of 6. So she's wondering if x over 3 being written is tantamount to now talking about all multiples of 3. So already that's, I think, well, I can't say anything about how common it is, but it's notable that she almost imagines the quantification. So clearly she's jumping from what I mean by reasoning about predicates, right? She sees this as referring to possibly all objects that have the property. Even though really writing that, of course, doesn't assert anything, but that's how she's interpreting it. The other thing that was interesting is, so A, her partner, sort of retorted and said, well, no, by the time we get to line 3, we already know that x is a multiple of 6 from the first line. So A is tracking how there's this progression through the text, and that then she uses this time metaphor already. We know from above that x is a multiple of 6, and so she's seeing, she's structuring this kind of directedness in the text of moving from one thing. Already this happens, then we find out this other thing. And so that it's this time component, and also the students would use words such as goal. So M used the word goal, A talked about already. There are these metaphors that they're putting into the text to make sense of this directedness from hypotheses to conclusions, or however you want to frame that. Moving to 1.2, M kind of paraphrased it of what is it trying to prove. They said proof 1.2 is not proving theorem 1. She said, I feel like it's trying to prove that just because it's divisible by 3 doesn't mean it's divisible by 6. And this is a pretty common kind of colloquial way to negate an if-then, is that you don't negate a conditional by saying P and not Q. You say if, then not always, or if, then not necessarily is the always the other one true. So again, it's interesting the meanings that just kind of come up as they talk about this, but I think this is a pretty nice paraphrase of proof 1.2. What also came out that was really interesting is, so this is where the computer science thing became really relevant. For M, she talked about how that first line, she thought of it as a for loop, that it was iterating through all the integers and returning the ones that make it true. So then when it says let x be a multiple of 3, it said that's iterating through and returning the multiples of 3. And this was a metaphor she began to use quite heavily and quite productively, building on her coding experience. Okay, A, on the other hand, had a different way of thinking about multiples. So let's talk a little bit about what A was bringing to the table. So she did interpret 1.3 rather productively. Here, now this is contraposition. So she's saying, I think it's saying, because if it's not a multiple of 3, then it's not a multiple of 6. And she did actually see that as equivalent to Theorem 1. She said this does prove Theorem 1, even though she had trouble articulating contrapositive equivalence exactly. She ended up, here was the way she tried to argue it. Basically, she said, well, okay, so if you're a multiple of 6, you have to be 3 times 2 times something. So she's imagining divisibility is, I can represent it as a factored out term. So if you're divisible by 6, I can multiply 6 times something. And she said that's 3 times 2 times something. So therefore, you have to be a multiple of 3. And so contrapositively, she says if you don't have 3, if you're not a multiple of 3, you can never be 3 times 2 times something. So she just sees how, yeah, those have to go together. And she made this like cake, baking a cake metaphor of, if you don't have flour, you can't make a cake. So if you don't have 3, you can't make a 6. That's sort of the way she conveyed it. So notice here in this context, this factoring out meaning was productive for A in her reasoning about the task. And that representation is going to be important when we move to proof 2. Another thing that was kind of interesting, though, is she said, oh, you know, actually, I know about this because just today in my stats class, my professor talked about this, meaning contraposition. And so she said, yeah, we went over this just today. It was something about like, you know, if you start a car, you've got gas, and if you don't have gas, the car won't start. But then when she tried to express in general terms what contraposition is, oh, I skipped a step there. What she actually said is she says, when A leads to B, B doesn't necessarily lead to A. So to me, as an expert, I would say, well, what you just explained here is not contraposition. That's actually that the converse is independent. But she was trying to explain herself and thinking about it. So notice, it'll be important as we move forward, she has a generalized statement here that the converse is not equivalent. A does. Even though she was trying to explain something else. But just keep that in mind. Also, an interesting thing about A, though, is it was very clear there wasn't a lot of separation between what the proof said and her own arguments for why the theorem was true. In trying to explain what the proof said, she would very quickly just jump into, here's my own argument about why it's a true fact. And for her, there wasn't this separation between the proof proving the theorem and her proving the theorem, because it was sort of this dialectic back and forth. Which is, again, very natural, it's very common, but it's an important aspect of trying to reason about logic to kind of maybe think about those two somewhat separately. Okay, so parsing by conditionality. Both students agreed that 2.1 proved theorem 2, so, and we won't really spend a lot of time on that for now. But once we got to proof 2.2, which is the proof of the converse, A thought that proof 2.2 did prove theorem 2, and it proved the converse. And M thought that proof 2.2 only proved the converse and not theorem 2. So they disagreed about that, and so we'll explore why they did that. So first off, why did A not distinguish the converse in the statement? Well, if you think about her factor out meaning, underneath the if part of theorem 2, she wrote this. Because if it's divisible, or a multiple of 2 and a multiple of 7, then she used her factor out idea to say, well, then I can represent the number this way. And if it's a multiple of 14, she wrote it this way. And at that point, do you agree? Those two are going to be pretty closely tied, right? So in her thinking, this factor out meaning made these two almost indistinguishable. And so it's very clear that she was so convinced of the biconditional nature of this relationship that then, yeah, the proof of the converse proves the theorem. They go together. The way I wrote about this years ago in studying another student's reasoning in geometry is just that she observes that they co-occur. These two things always happen together. And there's no direction to the relationship. They just both happen or they both don't, right? Those are the two options. And it's rooted in her meaning for the divisibility or multiples. Whereas M, on the other hand, in her thinking about the task, she started thinking this directed way. So she uses this chronological language. You start and you finish. And she said, she pointed out that the conditional statement, theorem 2, goes from 2 and 7 to 14, or whatever language she used at various points, and the proof goes from 14 to 2 and 7. So she thought that flip-flop meant that they were different. Okay, so then what we did is we then modified proof 2 by replacing all the numbers 2 and 7 and 14 with 6, 4, and 24. And then I had them go through, and this was mostly the second session, that we went through and replaced all the instances of 2 with 4 and 7 with 6 and 14 with 24. Now, pretty quickly, when I said 6 and 4, they anticipated the third number should be 12. Their knowledge of multiples was pretty rich. And so that, I said, well, okay, yeah, but let's do 24 and see what happens. Just bear with me. And so after we had worked through it, we realized these relationships. So M was blue, and she believed this proof proved this theorem, this proof proved this theorem. And then A was green, so she believed proof 2.1 proved the theorem, proof 2.2 proved both. And then we were looking at, okay, but what happens when we change the numbers? And when we change the numbers, we see that this theorem is now false, this proof fails, and we identified the part where it fails. And then this proof works, this theorem's true, and we get that. So naturally, you may notice what I was setting up here. Is the fundamental theorem of logic, or fundamental warrant of logic, going to be operative here? That if changing the number, how much more structurally parallel could two arguments be? All we did is change the numbers, right? And so the question is, would A in particular think, well, look, if changing the numbers, this proof should not prove a false theorem, therefore maybe this doesn't work. That was sort of the question I at least wanted to ask. Moreover, what I was really aiming at in this task sequence is, can we get this structure tight enough that she can see the analogy between the arguments to understand what this would convey? And it turns out she did. She knew exactly what I was, she saw the game I was playing. So as I'm drawing the arrows, I said, now last time you believed this, and she said, yes, I still do. But let's see her response. She said, just because of how the numbers are. So in other words, on those top two, she said, yes, you get that diagonal arrow because of the numbers. If you change the numbers, not the same. Switching it up, putting other numbers in, you end up with new theorems, then no. And down here she's saying, I see how this works. I see the analogy you're making. But her contention was, just because this arrow would be a problem with those numbers tells me nothing about that arrow. She said they're different numbers, different arguments, doesn't matter. Does that make sense? So I take that as her rejecting the fundamental warrant of logic in this application. So for me, what was powerful about this is A, that she recognized it. She saw the question. But for her, the structural parallels between the arguments doesn't mean that everything is parallel. Because when you change the numbers, the relationships are different. And so the arguments are as formally similar as possible. And even, remember on day one, she had said, made that statement about converse independence, right? And yet still, her conviction about this relationship between 2, 7, and 14 was so strong that she just closely associated all the terms. And so, moreover, I think part of what's going on here is that, again, there was not a clear separation for her between what the proofs say and what she was convinced of by her own arguments. Let's talk briefly about what M did in a similar way. So M then, she did not believe in that diagonal arrow. She thought proof 2.2 did not prove theorem 2, and I was asking her about why. And her argument was basically that it would end up being tautological. And what she means is, if the proof starts out assuming you have a multiple of 14, and then the goal of the theorem is you have a multiple of 14, then if you sort of concatenate that, abbreviate that, what do you get? If you have a multiple of 14, then it's a multiple of 14. She said, well, that's kind of obvious, so you're not proving anything. So her argument, because she viewed the theorem as directed and the proof as directed, then by concatenating this like two directions, she said you're going from 14 to 14, and that's tautological. That was sort of the heart of her argument. And you wouldn't need to prove that because it would always be true. It's more of a law than a proof. So I thought that was an interesting argument that she came up with to convey this. So let's talk then about her meanings. So I would claim M's meaning for conditional truth, at least what she's evoking in this task. I'm not going to say this is how she always thinks. Maybe more closely approximates warranted conditional. And it's this very, even though she probably doesn't have as strong of a meaning for the idea of a valid warrant, she definitely is thinking of this directed sense. And so, and that came out across a lot of her reasoning. Yeah, okay. So, discussion. I think I'm actually sort of on time here. So let's unpack a little bit of what I see in this data and where I think it reflects on at least laying the groundwork for the meanings that students draw upon in this context. So first, I don't have time to present it, but I do have some evidence through the completed teaching experiments that students can use subset meanings after we teach them, or they can use this warranted conditional meaning to resolve the initial problem I posed to you. How do we distinguish the force of the proof, the converse, from the original statement in a biconditional situation? And students were able to make arguments in both ways. And the way that you resolve it with the subset conditional is basically if a conditional means one subset relation and the other conditional means the other subset relation, they're both true, but they have different meanings. They convey different information. And that's how one proof can prove one condition direction while the theorem says the other. And that's how it allows students to distinguish those. Using the warranted conditional, what I've observed at least to seem to be at the core of that is this notion of direction. So this idea that if then moves from one to the other. And as I showed at the beginning, depending on whether students are reasoning more about properties or about predicates, they see that direction as sort of, different directions. I mean, there's different kind of ways you can construe that relationship. But for students like M who have a very strong sense that goes from if to then, that can be a productive way of dealing with it. What I don't see a lot of in talking with these students is the textbook meaning. The textbook meaning of sort of truth leading to truth is at least what I don't see students sort of articulating that in a way that they can really harness for explanations in the same way. And I think there's a couple reasons for that. In a recent paper here, I discussed this idea I call the pronominal sense of reference. And it's basically this. When I talk about rectangleness, students think that means I'm pointing at rectangles. So a pronoun, the pronominal means like a pronoun. So when I say he, that points to a person, right? In the same way, when you say rectangle, students assume that points to a rectangle. So what students don't think is, it's not natural to have rectangle point to be Yao and simply return false. I mean, that's just a funny way of thinking about it. Do you know what I mean? Rectangle points to rectangles. It doesn't point to all the other stuff and return a false output. So this idea of a truth function that ranges over all objects and returns truths and falses is a very odd, esoteric way of dealing with it. And it's not a good model for how students naively read these things. So that's where the truth functional approach I find to really not be very intuitive to students because of this when you say, so classically Frege was the one who tried to think about the difference between a sentence and its assertion. So if I say I want a ham sandwich, or you say I want a ham sandwich is true, what's the difference between those two? Because when I say I want a ham sandwich, aren't I kind of in speech acts, I'm saying it's true, right? I mean, I wouldn't say it otherwise, right? So this whole notion in logic, there's this artificiality that comes in when we start talking about truth that I find is part of my way of making sense of why I think I don't see truth leading to truth to be a meaning that students seem to evoke very naturally. Now, that's not to say you couldn't develop a teaching sequence where it might be functional. I have no idea about that. I'm not making a claim. But I have reason to believe why I think it feels more foreign than we maybe give it credit for when it's in all these intro to proof textbooks. That's the claim I'm making. Moreover, what I find really interesting and compelling here is that A, who is a very precocious student, was very aware of the mathematics at play. She still recognized the way I was setting up this question about the fundamental warrant of logic. She didn't state it that way, but she saw the analogy I made, and she very explicitly said, no, it doesn't have force here. That doesn't, the bottom proof statement pairs don't reflect on the top. They don't determine what works there, even though the proofs were about as parallel as they could be. So I thought that was really fascinating, and this is something I want to continue to pursue, is not so much saying that A is right, but as much as saying, how do we engage students in thinking about that as an idea of logic, and why that is in fact a useful way to try to analyze arguments. How would we begin to make the fundamental warrant of logic accessible to students and in some way compelling? So yeah, and I want to continue to explore how the subset meaning is productive in this context. With that said, some things that I'm learning in terms of their more specific ways of reasoning. It's really important to think about the scope of claims. So we have these really subtle cues, like the first line says let x be a multiple of 6. The last line says thus x is a multiple of 3. But underneath that, there's the assumption that the let line is quantified. It refers to any multiple of 6, whereas the last line, because the variable is bound and it already existed in the first line, does not refer to any multiple of 3. It instead says no, over the scope of x in the first line, the last property always holds. And there's some subtlety there, right? So how do we want students to construct those kind of subtleties in a productive way? And that's something that I'm trying to build into this teaching sequence. The other thing that I noticed about M's way of reasoning that was really fruitful for her was when she talked about the 2 and 7 versus the 14, she talked about how she would code it with 4 loops. And the 2 and the 7 was a nested loop for her. You would first run a loop to return if it's a multiple of 2. Then within that, you would run a second loop to return if it's a multiple of 7, versus the loop for 14 is a single loop. And what that allowed her to understand implicitly is these are different predicates, even though they have the same truth set. They refer to the same object, but they are different things. And therefore, you can have this directed relationship between these two predicates because they're distinct while still in agreement. Versus A's meaning of factoring out did not really allow her to create much separation between the two predicates, in part because they share truth sets. They refer to the same objects. And so that, I think, was productive. And again, I'm not going to teach every student to code, but it makes me wonder what is the essential value of this idea of sort of recognizing the predicate as both related to but distinct from its truth set in some various ways, and how do students build those kind of meanings. And then also thinking about relationships between generality and arbitrarity. So this is sort of where we're headed. But with that said, I think I've exhausted my time, so thank you.
Do we have time for questions?
This isn't a question, but are you familiar with Elise Lockwood's career grant?
All this stuff about combinatorics and ways of counting
and computing. Like there's this interesting new bridge now between understanding particular areas of mathematics through coding and vice versa. It seems like this is so applicable to what you're doing.
Yeah, no, what I'll say is I think I'm not as familiar with that extension of what she did. I think I know some of what she did on the modeling side, but less on the computing side. Well, I don't
That's
know.
new now, because it's a new project, but the whole purpose and idea of the project is that there are, I guess the thesis is that there are ways in which we can come to understand mathematical relations in different and more productive ways through computing activities. And she's literally doing just that thing. You're like, I'm not going to teach them all the code, but that's like what the project is teaching them to code as a avenue for learning combinatorics, and everything that you were talking about with all of these logic statements just, oh my goodness, it feels so compatible with coding. It just makes me wonder if this could be an outcropping of this new bridge between computing and mathematics.
Yeah. Well, I think, there are obviously really deep connections between working with coding as a formal language or as a formal system.
And learning logic.
And thinking, and because logic is trying to render language as this pseudo-formal system, right?
Yeah.
And that's, of course, why I don't believe that logic is in language the way that some people want to believe it is, because I believe natural language is much more fluid. But there is this natural relationship there. And an example of why I've not wanted to go down that road, I guess, is when I jump into geometry, then all of a sudden this coding for loop thing is a lot less accessible, because she can imagine iterating through the integers.
Right.
You can't imagine iterating through all the quadrilaterals.
Right.
And so that metaphor dropped as soon as we went to geometry.
Yeah.
But I still want them to imagine categoricity, that for any well-formed predicate, I can imagine forming the truth set, even without populating it.
Yeah.
So that's why I've gone a different direction, but there's certainly huge avenues that could be pursued, absolutely. As long as you stick with the domains in which those things translate well. And I'm eager to learn more
But it
about
just
where
has
she
me
has
thinking
gone.
about the ways in which structuring students' experiences through thinking about the formal logic of coding can also influence their understanding of these proof structures as well. I don't know, it's a really open question, but.
Yeah. And I think, one of the ways I've talked about the earlier part of this project in terms of just students thinking about truth conditions, not the proof stuff, is that for a lot of students, the first step is getting them thinking about languaging. That when they understand that the game I'm playing is thinking about language, as opposed to language always being the kind of portal through which I talk about everything, I look at everything else. When they recognize that language is the object of reflection here, that's part of what I mean by raising the question of logic before we give them the answers. And I do think computer science trains that they are going to be thinking about at least about certain kinds of language naturally as the object of study, right? That you both do the program, those go in tandem. And that's, again, a very strong parallel to what I'm trying to do, which is that, when students first engage in this stuff, they always think that the question at hand is about multiples. But of course, my goal is for them to use that as a mirror to reflect back on arguing, right, proving. And that shift in their focus and their awareness of what they're attending to in the situation is a big part of what I'm trying to generate. And I want to be careful to say I don't think my way of doing it is the only way to do it. I know it's not. I have my motivations for why I'm going down the path I am, but I do think coding is a huge avenue by which you could explore a lot of this stuff. And I should pick Elisa's brain more. We all should. Everybody should always pick Elisa's brain more. So, good. Thank you.